Entropy. So entropy is basically a synonym for chaos or disorder. This shows us that there's energy with a system and its surroundings. And the ability to go from this situation of high energy to low energy is exactly what entropy is about. Entropy does not like organization, it doesn't like stored energy, it likes to release that energy. You might see in physics a difference between potential and kinetic energy. Potential energy is stored energy, kinetic energy is energy of movement. And you can imagine that gas sitting in your tank wants to be blown up. It wants to go to that engine and be burnt and combusted. So anytime we can take a highly organized system and disperse it into the surroundings, that's what entropy wants to do, and entropy is always winning in the universe. So you can imagine a good example or analogy for entropy is a cleaned room. A parent might spend hours cleaning out closets and picking up dirty clothes and making beds and organizing toy boxes or bookshelves, and then 5 minutes later a toddler might destroy everything in 5 minutes that took 5 hours to organize. That's exactly what entropy is. This idea that if you get a brand new car, as soon as you drive down the road, you get rock chips or birds poop on it, whatever. That's what entropy is. The ability for things to stay nice, to stay organized, is not what the universe wants. The universe likes chaos and disorder. That's a very important principle of thermodynamics that you'll learn about in Gen Chem even more. So if we apply this to solutions, you can realize that this nice organized cube is perfectly organized, perfectly packed together, much like that closet, much like that toy box or that bookshelf. Entropy wants to toss that solute into a solvent and then create chaos, create a solution. So the ability for the solution to be made from something that is highly organized here and go to something that is pretty disorganized over here is a lot of the energy values that we think about behind the scenes for when we're breaking bonds versus making bonds, or at least breaking attractions and then forming new attractions. So you can imagine that it's just like a clean room. That clean room is going to get dirty in a hurry, and that's what happens from clean room to dirty room by analogy to our solution. So the solute breaks apart, the solvent separates, and then we have a solution. And that's exactly what we talked about in our previous video. We're just talking about it now in terms of energy, and that energy is typically entropy driven. As we look at solubility with solutions, we can think about some very lifelike examples to help recognize these ideas that we don't have to really memorize them. So solubility is the amount of solute you can put in the solvent. Basically, how much sugar can you put in your tea? How much salt could you put in the ocean, so to speak? And it's all really three factors that determine that idea. Temperature is one of the big ones. Depending on the type of solution, though, temperatures that are high are good, temperatures that are low could be good in certain situations. Identity of the solute would be polar loves polar, like dissolves like, nonpolar loves nonpolar. So things like oil and water not mixing is because oil is nonpolar and water is polar. They're not like each other, so they're not going to dissolve in each other. And then pressure, really just a feature of gases, which is also our chapter, in our final chapter next week. So as we look at solids and liquids, this first idea of solubility, notice in both of these pictures, as solubility increases with temperature. So notice this curve kind of goes up. And that's because temperature is going up, so solubility is going up. So high temperature is high solubility if you're a solid and a liquid. That really just tells us that if you have, say, sugar and you put it into water, if you boil that water, you can put in more sugar. If you were to have ice cold water, most of that sugar would settle to the bottom. An easy way to think about that is getting tea at a restaurant. If they bring you iced tea with no sugar in it and you want sweet tea, then you're going to put sugar packets in there. Problem is, as soon as you dump it in, all the sugar sinks to the bottom, and then you stir that sugar in for about 30 minutes to 45 minutes. By the time you're ready to leave the restaurant, only then do you get a little bit of sugar dissolved in that tea, and that's because it's so cold. A disadvantage to solids and liquids is you have two steps that require energy. And if you're ice cold, there isn't much energy to take. So sugar has a very hard time breaking apart from itself because there's not enough energy in the solution without you stirring it fast enough, quick enough, and long enough to give you that energy to get that solute step to behave. So separating the solute is difficult, especially when it's cold. It's even more difficult to separate the water without stirring because it too requires energy, and if it's got ice in it, there isn't much energy there. But if you had hot tea, you could put in as much sugar as you want because it already has the energy needed to do those first two steps just fine. Everything is backwards, though, when we look at gases and liquids. Gases and liquids would be a good idea to think about soda. If you want your soda to have a high solubility of carbon dioxide, so carbonation, in your soda, you want it to be fizzy, you want to keep that soda cold. If you've ever been to a birthday party with soda sitting on a table out in the sun with the cap off, it loses its solubility of carbon dioxide very quickly and it goes flat, and you have a very thick, a very sweet Kool-Aid at that point. So for gases and liquids, so think of CO2 in your soda. We want low temperatures to give high solubility. And this is exactly why fountain sodas are sold next to ice machines. This is exactly why most sodas, when you purchase them at a gas station, they're going to be in those refrigerators. That's going to keep those sodas fizzy a whole lot longer. So either one of these ideas should be pretty straightforward. Most people have dealt with tea and recognize its ability to, or even coffee, to go in just fine when it's hot, but not so easily when it's cold, when it's iced, for sure. And then most people have had experience with regular soda or diet soda to realize that if you keep them cold, they last longer, they stay fizzy longer. That also being true. Like dissolves like takes us back to exam 3, specifically with intermolecular forces. So this is really where we get into those definitions one more time with the electronegativity table. So remember when they say polar molecules, that means 0.5 or larger in electronegativity difference. And they're going to love other molecules that are 0.5 or larger because they're going to have partial positive and negative charges, and they're going to have attractions because of that. So water loves molecules like sugar because they have OHs. Water has OHs. Sugars have alcohols that have OHs, and that's a perfect combination. Salt has positive and negative ions. Water has partial positive and negative charges that can attract those positive and negative ions. So polar loves polar, polar loves ions because they have attractions between those partial and full charges. Nonpolar molecules, by definition, that's going to be those that are less than 0.5 in electronegativity. Those are going to be things like hydrocarbons, things like gas molecules like O2 and N2, even CO2 by cancellation. You can put oil and gasoline for mixed oil engines like lawnmowers and chainsaws and so forth because oil is nonpolar and so is gasoline. When you throw water into oil, it doesn't mix, and that's because water is polar and oil is nonpolar. And those two are not like each other, so they're not going to mix in each other. So these ideas are nothing new. They're just a revisit from the Intermolecular Forces chapter in Exam 3. As we look at gases and liquids, we're looking at, again, soda. So you can imagine that if you twist the cap off the soda, so imagine this is the cap of the soda. As you twist that, you're releasing the CO2. That's where you hear that little tss noise every time you open it. Every time you put the cap on, or when it's put on for the very first time, you're forcing all those molecules into solution by pressurizing them. So for gases and liquids, there's two features that we mentioned. They like low temperature. That's why it's important to keep your soda cold. They also like high pressure, so they like you to keep the cap on. So it's to your benefit to take big drinks of soda, because then you open and close that cap less frequently. It also gives your teeth less rinsings of acids that are in that soda, which will make your dentist a little bit happy in the end as well. We could do some conversions using this concept of saturating solutions. We can use this information from our solubility table concerning water from earlier. It shows that at 20 degrees, at room temperature, basically, you can put 203.9 grams of sugar per 100 grams of water. So this is just showing you you can put this much sugar into this much water. So you can put double the amount of weight of sugar into water at room temperature. But then you can realize you can almost quadruple that. If you boil the water, you can definitely add a tremendous amount of sugar in there. And that's because there's plenty of energy for that solute and solvent separation steps. However, if you make it in ice cold water, you're way down here. So as long as our units cancel from the grams of water to our conversion, we can get an answer just like they show here. I decided not to use many of these kinds of calculations on the exam because they're kind of repetitive from our earlier chapter with the metric system. So don't expect to see these too much, but it is really no different than the metric conversions we've seen before, now just using a solubility conversion of grams to grams. You can imagine we can use that same table in this situation to calculate tons. So if we're making hummingbird food for in a factory, we can use the conversion of pounds and grams. We can use the conversion of tons and pounds. But again, this is a lot of that English to English, metric to English kinds of conversions we would have seen in the metric system. So it's not something that I'm going to hit on again in this chapter to any great degree. It is in the notes, and I do show you that you can cancel tons just fine. You can cancel pounds just fine. This is the 454 grams per pound that we give you on the exam to use. It cancels with grams of water, and then based on this conversion from the table, we can use to get to the amount of grams of sugar needed to make a ton of hummingbird food in this case. But again, very similar to previous conversions. What we're going to focus on mostly in this chapter mathematically will be molarity, and it'll be percentages, not these kinds of metric conversions with solubility. Speaking of which, molarity is a major concept for this chapter, so we'll catch that in the next video. See you then.